Okay, let's start. Good morning. How are we all doing? Problem set 3 was a bit rough, I guess. Yeah.
That week was a little bit busy for me, but I probably could have worked harder.
Yeah, you guys have like a bunch of other exams and stuff as well too. Yeah. Yeah. Well, I mean, part of going to college is to learn about what your priorities are, really. Okay. So on Friday we have our first midterm. So today we have regular class, tomorrow too, and then on Wednesday we're going to have a review. I'm not recording anything. I'm not going to record anything and stuff, so it's going to be all, private in a sense. So today, what I'd like to do is to cover certain structure theorems about continuous functions, starting with the intermediate value theorem. We would like to understand how continuity interacts with intervals. We would like to be able to say something like, if I were to take an interval, then under a continuous function, its image too is an interval, right? Stuff like this. Before that, though, I want to mention this AI thing, Deepseek. How many of you have looked into this? Over the weekend, I experimented a little bit with this. It's this new sort of model that came from this Chinese company, and like it's all the people in the United States are sort of concerned about this right now because they apparently Deepseek stole their work. But in any event, I was very impressed. So right now what you can do with this, I'm not saying you should, but you can feed, for instance, one of the PDF files, the problem sets. It can read everything, generate for you formal solutions, and then you can even ask it to put it in sort of like code so that you can sort of type your solutions on the computer, on overleaf and stuff like that. There's a certain sort of language that I use that pretty much everyone in sciences use to sort of come up with or write down scientific or technical documents. So for instance this. So it can generate the code for that as well. And even though it is not 100% perfect, from my initial preliminary analysis, I can say that it's an A, okay? So Deepseek would probably get an A from this class. So that's concerning. I wasn't expecting AI to be developing this fast. And of course, part of it is that I want this class to be something that is not obsolete. Obviously, some of you need to take this class to graduate and stuff like that, but also I want you to have something that's going to be helpful in your life later on, in your career or something like that. And it seems like by the time you graduate, AI is going to be even more incorporated into your work. Possibly the job that you were hoping you'll have is not going to be there anymore. I mean, that might be applicable to me as well. But so I am thinking of ways to sort of incorporate more AI stuff into the problem sets in the sense of, oh, maybe we can sort of come up with certain problems that are hard, but you're allowed to use, collaborate with the AI, with Deepseek or whatever, so that you guys get accustomed to this as well. Because I think at this point, it's not really a luxury for regular people to not be aware of these kind of things and not to use these type of things. So I would be very interested in sort of structural changes that you could recommend regarding problem sets. How to incorporate more AI. How can I make it more encouraging for you to sort of look into these kind of things and perhaps use them. Okay, so maybe if you have ideas, you can send me emails, or if more people have ideas, maybe we can sort of have a meeting or something like that. Anyway, so that's something. Okay. Of course, like now that Deepseek did something, and then OpenAI has these 5 other models that are somewhat similar and stuff like that, and ChatGPT is also not that bad, but I was really surprised by this Deepseek thing. I also fed it a graduate level problem set. It didn't do as well, but still, it's not terrible. So, and it's all about sort of understanding the slope, right? Like the exponential growth, it's hard to understand for humans, they say. So I was surprised. Anyway, any questions about anything? So here's a definition. If I have two metric spaces x and y, I'm going to call a continuous function f from x to y this is a new word, homeomorphism. Okay? From x to y, well, if it is continuous and it is a continuous inverse, and that's it. So I want a function. I want it to have a functional inverse, but I want the inverse to be continuous as well. And in this case, we're going to say x and y are homeomorphic metric spaces. So morph means sort of structure or shape. Homeo is about continuity, has the same continuity structure in a sense. That's the idea. Later on, we're going to see another word, which is very similar to this. It's going to be diffeomorphism. That's going to be about preserving the differentiable structure. So these are important terms in contemporary math, and so I wanted to introduce this. Okay, so let me set up some notation, because all the theorems, we are going to study 3 theorems today. All of them are, they use the same sort of setup. I'm going to have I to be a closed and bounded interval. So it's from lambda to rho. I want these numbers to be finite numbers, but they might be the same. So if they are the same, I just mean it's a point, right? And then I'm going to take a function. This was a notation for the set of functions for me. From I taking real values. Okay? I don't want to keep writing this for each statement we're going to study today. So I wanted to factor out the hypotheses. So statement 1 is the intermediate value theorem. It basically says that, well, a continuous function assumes every single value in between, ultimately. So if f is C0, recall this was my notation for a continuous function. Let's write it like this. Then maybe even before stating the statement, let me draw a picture. What is the intermediate value theorem? It says something like this. I'm going to draw the box. Here's lambda. Here's rho. And it takes some value here and some value here. Let's say that f of lambda is this point and f of rho is this point. I'm just drawing the graph. I want to say something like any point in between has a pre-image. Could be multiple, but at least one. Then, so one thing you can do is the following. You can say, oh, I'm going to look at the minimum of the value that f takes at the endpoints, and then I'm going to compare it to the max. Then, so for any y inside the interval with endpoints min of f of lambda, f of rho, and max of f of lambda, f of rho, there is an x in the interval such that f of x equals y. Why do I do this? Because in our notation, the number that you put first is the smaller possibly one, right? So, but I don't know if f of lambda or f of rho is, which one is larger. So this is like a faster way of writing this. So if you want to be even more fast, what you can say is that you can call this interval, let's call it J. You can just say that J is a subset of the image. This is a compressed way of writing the same thing. Okay. So what is the idea? The idea is this. Let's assume f of lambda is strictly less than f of rho, so that you have a picture like this. Okay? So you start here, you go there. Okay? And from calculus, we know that continuous functions should have graphs that you're able to draw without lifting the pen. And so if I were to have a height here, right? If I'm starting here and ending there, eventually I'm going to hit it, at least at one point. That's what this says. But the point is to prove it, right? So here's a phrase that is very common in math. WLOG, or without loss of generality. Now there's a bunch of statements here that are like compressed. So I can just make some simplifying assumptions. And even though they are simplifying assumptions, ultimately what you're simplifying is not the main content of the theorem, but rather sort of some technicalities. So proof. So this stands for without loss of generality. Assume that f of lambda is strictly less than f of rho. I should also mention, so what does this mean? This means that you're telegraphing to the audience that while you're aware that you're looking at a case, this case is pretty much the general case, so you don't need to worry about the other cases. And of course, this could be abused as well, right? So always be careful about whether or not something is without loss of generality. There are, in fact, even certain, let's say, schools of mathematical thought that really focuses on this idea. Like, what exactly does it mean to switch over to without loss of generality? How does that exactly work? And they have a geometric understanding of this and stuff like that. Very interesting stuff. But of course, for us, it's not important. So let's say this. What do I need to do? So in this case, what happens is that J becomes f of lambda to f of rho. Okay, so let me draw the picture. Okay, I'm just going to draw the graph. This is lambda, this is rho. This is f of lambda. This is f of rho. Okay, so I'm saying that my graph hits this point. It also hits this point. Now the statement says, for any y between these two values, so I need to take a y. So let So here it is. Now technically, I could have chosen y to be equal to f of lambda or f of rho as well, but this is sort of the typical picture. Okay? In the caricature, I'm trying to sort of draw something that actually is easy to visualize. What do I need? I need an x somewhere here. So I need an x such that my graph passes through this point. So I need to identify where x is. Maybe there are multiple, but I need at least one. Any guesses as to how to argue about this? Any ideas?
If the graph doesn't pass through y, then there's no way it can get to f of rho, because it's continuous.
Well, yes, but that's what we're trying to prove.
Well, yeah, but like, I don't know, maybe proof by contradiction.
Yeah, I mean.
If it doesn't pass through y, then such and such is impossible, but I don't know how to actually do that.
Yeah, we need an actionable thing, okay?
Yeah.
So what you can do is this, okay? I want to think of the x coordinate as the independent variable, so the time. And so I know that when time is lambda, I'm starting here. And if I go all the way, I'm up here, okay? So what I can do is I can wait, okay? I can say, I'm just going to keep waiting, okay? Until I pass this. That's going to give me a subset. Put A to be the set of all those x's such that f of x is bounded from above by y. That's a subset. Okay. Lambda is in this. So it is not empty. Rho is an upper bound because it's a subset of I after all. Well, by the completeness axiom, I know that the sup of A exists as a number, and it cannot be larger than rho. In other words, it's an element in I. Let me call that sup alpha. This exists. In a sense, this is the first time, heuristically speaking, that I'm hitting the height y. Right. So the sup is basically it's the max, right? That's sort of like the heuristic. And I'm saying I'm just going to wait until I reach this height. Okay? I might reach it multiple times, but there's a first time I reach it. Hopefully. The claim is, what we need to show is that f of alpha equals y. So the first time I reach y is the first time I reach y, ultimately. So when I'm saying that, oh, this alpha should be the first time I'm reaching y, I'm actually assuming this claim. Okay? Now we need to prove this claim to verify that the heuristic is actually true. Okay? Any questions about this? As I'm getting a better idea as to where you guys sort of struggle in writing proofs, I'm sort of seeing more sort of appropriate ways where we sort of expand on. Okay. So I have a picture, I had an idea, and I'm sort of transforming that idea into something rigorous. Yes?
Wouldn't alpha be the last time it hits y?
No, because, so imagine something like this. I'm just going to draw a graph. So let's say this is y. I'm starting here and there. Alpha would be this. Oh, you're right. You're right. It's the last time. You're right. You're right. Okay. Fair enough. Exactly. So in this picture, for instance, what is this set A? It includes this part, and then it dips. It includes this part, and then it dips. It includes this part, which means that alpha should be this. You're right. Okay. I mean, it's not going to matter for the proof, but yes. Do we all understand this? Okay. I think in my head I was sort of literally starting here and sort of taking larger and larger intervals. That would also work, of course, but what I wrote down is not what I interpreted. Okay. So alpha is a sup of a certain set. I'm going to leave it to you as an exercise to realize that because alpha is the sup, I can come up with an increasing, strictly increasing sequence in A that converges to alpha. Okay? So you need to open up the definition of sup, and you need to farm sort of like a sequence. There is an X bullet in A, strictly increasing, converging to alpha. Okay. The point here is that for any n, sup of A minus 1 over n is not an upper bound, which means that there has to be a value in A that exceeds this. And you keep sort of iterating this idea. Okay. I assume that f is continuous, which means that the limits are preserved. Since f is continuous. Well, X bullet is a sequence in A. By definition, that means that for any n, f of x sub n is bounded by y. Since this is a sequence in A, for any n, I have that f of x sub n is bounded by y. And then by the squeeze theorem, we can say that the limit then is also bounded by y. So we're almost done. We need to show the other inequality. I'm going to say, suppose it's not equal, which means that, say that this is strictly less. Say f of alpha is a strictly less number than y. Okay. So what is going on here? In our picture, somewhere here is alpha. And then we came up with a sequence that converges to alpha inside A. Right, so these are all x sub n's. What are we assuming? We're assuming that if I were to look at the values of f, here, maybe something like this happens. That's what I'm assuming. Okay? So let's say that this is what is happening. I'm trying to get a contradiction. Okay. Well, what I can do is this. I can use the continuity of f at alpha, okay, to sort of get something from the epsilon delta. So you see, because in this hypothesis, I'm assuming that f of alpha is strictly less than y, that means that there is some thickness here. So if I were to choose my epsilon smaller than this, let's say y minus f of alpha, I guess divided by, y plus f of alpha divided by 2, so their average, that would give me an epsilon. But then by the continuity of f at alpha, what I can say is that there's a delta somewhere here. So alpha minus delta, alpha plus delta, such that this open interval is sent to something here. Right? That's sort of the geometric idea behind continuity. So this little piece would contain the graph of f. Does this make sense? I'm going to write this more formally in a second, but this is the heuristic. Okay? F is continuous at alpha. So for, what did I do? For epsilon equals the average of f of alpha and y, this is a positive number after all. There is a delta such that for any x here, if x is delta close to alpha, then f of x is epsilon close to f of alpha. But this is a contradiction, okay? Because of the following. Look at this picture. Based on what I said, the idea is that no matter which value I plug in to f in this interval, in this small interval near alpha, its image is going to be in this box. In particular, it's going to be less than y. But then if I were to take this value, for instance, alpha plus delta over 2, well, that's going to be under f sent to some value that is strictly less than y. In particular, that value has to be in A. But it's also strictly greater than its sup, which cannot happen. Okay? So f of alpha plus delta over 2, so what is it? Minus f of alpha in absolute value is bounded by this guy. And then simplifying and blah, blah, blah. So you need to open this up, do things. This gives that alpha plus delta over 2 is an A. This cannot happen because alpha is a sup of A. It's an upper bound. Which is a contradiction. Which means that this cannot happen. In other words, f of alpha has to be equal to y on the nose. Any questions about this argument? Okay, so that's the first statement. Second statement is this. Again, I have an I from lambda to rho. I have a function f on it, taking real values. This has two parts. Same setup. First part says this. If f is continuous, then its image is an interval. It's a closed and bounded interval. Then so I can write it like this. F of I equals the interval from min of f to the max of f. We had talked about how a continuous function on a closed and bounded interval attains its min and max. So these are well-defined numbers. They are finite numbers. I'm saying that you're getting everything in between. And then second is sort of like the other way around in a sense. If f is strictly increasing or decreasing, and its image is a closed and bounded interval, let's write it like this. And again, maybe L and R are the same, so it's a point. It could be a point, doesn't matter. Then, in fact, I can rewind this statement and say that f is continuous. So we're playing with three ideas. One of them is continuity. The other one is monotonicity, strict increasing, strict decreasing. Third is whether or not the function takes intervals to intervals. These are three sort of related topics. We're trying to see how they are sort of situated compared to each other. Now for the first part, I'm just going to draw a picture, and I'm going to leave it to you to formalize the idea. Let me draw the picture. This is lambda, this is rho. This is the min, this is the max. Maybe I should use a different color. This is the max. Okay, so we know by the extreme value theorem that there is at least one point here, somewhere here, let's say, where f takes this minimum value. Okay, and then there's some other point, maybe here, doesn't matter, somewhere here, where f takes the maximum value also. But then, by the intermediate value theorem, I know that I can attain any value in between these two values inside this. Okay? Okay. And of course, I I cannot obtain any value that is less than the minimum and more than the maximum, which means that the image has to be equal to this. That's the proof. The exercise is to formalize this idea. Write it down explicitly. It's a very nice exercise. Okay, so that's the first part. Second part is slightly more tricky. Let's assume that f is strictly increasing and the image is an interval. So again, let's draw the picture. Here's lambda, here's rho, here's L, here's R. Saying, because f is strictly increasing, and L is in the image, well, it can only attain this value at lambda. And likewise, f can attain the value rho, R exactly at rho, and no other point. And what is strictly increasing? Strictly increasing means the following. If x1 is strictly less than x2, then their images have the same property. Goes up. Now note that in calculus, typically you would learn something like, oh, the derivative has to be positive or something, okay? But at this point, we're not talking about differentiability. We don't know if this function is differentiable. Typically, functions are not differentiable, in fact. If you were to think about something like Brownian motion, most functions fail to be differentiable. But still, we can make sense of what it means for a function to be increasing. Okay, now what do I need to do? I need to show that this guy is continuous. That's the conclusion. Well, continuity is a local concept, which means that in order for f to be continuous everywhere, it has to be continuous at x for any x. So I can take a point x, somewhere here. Well, let's say that f is not continuous there. Writing the definition in logical form and then reverting it, you get the following. So there is an epsilon 0 for any n, for any delta. There is an x, let me call this x star actually. There's an x such that the difference, so the distance between x and x star is bounded by delta, but the distance between f of x and f of x star is bounded from below by epsilon 0. Again, fixing this epsilon 0, you can keep taking smaller and smaller deltas to get a sequence that converges to x star, whose image stays away from f of x star. So there's a sequence, x bullet, converging to x star, such that for any n, f of x sub n minus f of x star is they are at least epsilon 0 away from each other. Okay. Now what is going on? What's going on is this. You have here your target, and your x bullet sequence gets closer and closer to this. However, let's say that this is the height. There's this epsilon 0. If you were to look at the images of each of these points in the sequence, they never hit this band. This is plus epsilon 0 minus epsilon 0. So they stay away. Okay. There are multiple ways of arguing about this. But let's say the following. At this point, we still haven't used the fact that f is strictly increasing. Well, what I can do is I can use this monotone subsequence lemma that I had given as an exercise. By monotone subsequence lemma, I know that there's a subsequence x prime, let's say, of x bullet that is monotone, or strictly increasing or strictly decreasing. There is and because x prime bullet is a subsequence of x bullet, it has to have the same limit. That was also an exercise that I had given. Because we assume that f is strictly increasing, again, without loss of generality, we can assume that x prime bullet is strictly increasing, actually. The other way around is similar. Well, that means that maybe I should be explicit here. The images are strictly increasing. And they're all bounded by the image of x star. Okay, so in this picture, what did I do? I have this x star, and I'm assuming that at this point f is not continuous. I took that assumption, turned it into a sequence. I came up with a sequence that converges to this x star. And then I sampled out a monotone sequence. Here, without loss of generality, I'm saying, let's assume that it is increasing. So it's this guy, perhaps. Okay, it's always going this way. But because f is strictly increasing, it must be the case that their images too are strictly increasing, like this. These are points in the graph. But because any f of x sub n is epsilon 0 away from f of x star, the same thing is true for their limit also. What am I saying? Oh, okay, yes. So the image sequence is a strictly increasing sequence that is bounded by the monotone convergence theorem. It has a limit. This guy is a sup of f of x sub n primes, which is bounded from above by f of x star. So they have to converge somewhere by MCT. So somewhere here. Okay, that's the limit. Well, but what I can do is I can use the final assumption that we have, namely that the image of f is everything. Which means that there is one height here. Okay, I can choose something in between that is closer than epsilon 0 to this target. It is a pre-image somewhere here. Okay. By definition, it cannot be to the right because f is increasing, so it has to be to the left. But if it is to the left, the sequence eventually is going to exceed it, and that gives a contradiction. Okay. 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 So the blue thing over there corresponds to this. Let's say, let y be between f of x star and f of x star minus epsilon 0. open. By this assumption and the strict increasing assumption, it must be the case that there is an x to the left of x star, such that f of x is equal to y. But then since x prime bullet converges to x star in an increasing manner, eventually I'm going to exceed this. Let me just leave it as is, a contradiction. This is a slightly tricky argument. Okay? And I think in the textbook they have a different argument. Yes?
I don't see a reason why it has to exceed it.
Well, here's the picture. This is my target. I'm saying this point that I chose is to the left of x star. And x prime bullet converges to this guy. There is no way for you to be bounded by this. After finite time, you're going to exceed it, because you have to be epsilon close to this.
I thought you were saying you were exceeding f of x star.
No, no, no.
Okay.
Any other questions about this? Okay, here's the final theorem where we have this homeomorphism property. This is the heaviest proof, I think, among these three sort of theorems that we're looking into today. The theorem says the following. If f is, same setup, if f is continuous and strictly increasing, then the same thing is true for the inverse as well. It has an inverse, and the same thing holds for the inverse. Same setup. If f is continuous and strictly increasing, or decreasing, of course, then f inverse exists as a function from the image of f to I, is continuous, and is strictly increasing or decreasing, depending on what you started with. In particular, that means that f is a homeomorphism. Homeo. Okay. The proof goes like this. One proof goes like this. F is strictly increasing, let's say. Well, that means that I'm going to leave that to as an exercise. It is an inverse, functional inverse, and that functional inverse too is strictly increasing. And is strictly increasing. Well, that means that f inverse is a strictly increasing function defined on an interval, which is the image of f after all, whose image itself is an interval. By the previous theorem, we have that f inverse is continuous. And that's the end. Okay. And I think that's a good place to stop. Thank you. I'll see you tomorrow. Okay, let's start. Good morning. I'm going to take attendance today. So this is the final class before the midterm, and you're responsible for topics that we're going to study today as well. So the majority of today I'd like to spend on establishing sets of continuous functions in particular as metric spaces. We had talked about how we're going to do this, and this is really an important thing. And then we're going to start talking about things like uniform convergence of sequences of functions. That's going to be very important for us. But before that, there's this different property. In the textbook, they spend a whole section on this, and rightfully so. It is important. It is called uniform continuity. But I think for us, it's rather a technical thing. So what I'm planning to do is I'm going to first discuss some exercises, and then I'm going to give you the statement of this theorem, and then we're going to leave it at that. And then maybe later on, if we have time, we're going to get back to this and prove it. Somehow, uniform continuity goes well with these ideas of Cauchy sequences and stuff. So we didn't spend too much time on Cauchy sequences. Likewise, I think it is appropriate to not spend too much time on uniform continuity. Okay. So first, the definition. I take a metric space X, and a subset A in it. Okay? I'm going to call that subset compact. I had, in fact, used this word. I said closed intervals, closed and bounded intervals are compact. Now I'm giving you a formal definition. Well, it has to satisfy this property, that any sequence in the subset has a subsequence that converges to some other point in A, possibly some other point in A. So in a sense, this notion of compactness really takes out this idea of Bolzano-Weierstrass and abstracts it out. In general, Bolzano-Weierstrass is not correct in the abstract setting of metric spaces, but whenever it is correct, well, you put it into a definition, basically. Okay? And so here are some nice exercises. The closed interval from 0 to 1 is compact according to this definition. The interval from 0 to 1, 0 included, 1 not included, is not compact. Okay? 0 to infinity is not compact, and likewise, the real line itself is not compact. Okay? All you need to do is to take these sequences and so on. Another nice exercise is that any compact metric space is complete. In other words, we didn't talk about this, but we didn't talk about it too much. Recall that a metric space is complete if any Cauchy sequence is convergent. So maybe I should write it, aka Cauchy sequences converge It's rather technical again. If you don't remember this and this stuff sound somewhat complicated to you, you don't need to worry too much about this. In the second class after this, the multivariable calculus class, you spend a lot of time understanding this notion of compactness. For us, it's not going to matter too much, at least at this stage, because you can just consider closed and bounded intervals. But it is there and important in general. Okay, so that's that. So the theorem says the following. I'm just going to state it, and we're going to skip the proof for now, because I'd rather spend time on function space. I take two metric spaces x and y, and a function f from x to y. Then the following holds. If f is uniformly continuous, then it is continuous. So uniform continuity, now I haven't defined it still, but it's a property that is, stronger than continuity. It's something that implies continuity, okay? So not only is it continuous, but in fact it is uniformly continuous. In a second I'm going to give you the definition. If f is continuous, and in addition x is compact, then f is also uniformly continuous. This is the second part. Then f is uniformly continuous. Oh, thank you. In particular, what this theorem says is that if you're looking at functions defined on a closed and bounded interval, like we were doing yesterday, for instance, in the context of intermediate value theorem and stuff, continuity and uniform continuity are the same thing. And because of that, I don't want to spend too much time on this. It is important, okay? It is important that certain functions are uniformly continuous and certain functions are not. But at this stage, I think it is rather too technical for us. So let me write that down. So in particular, any continuous f defined on I into R, and I, as before, is a closed and bounded interval, possibly consisting of only one point, is uniformly continuous. Okay. Since we're really interested in functions like this, and since we have this sort of general statement, I think I'd rather spend more time on other things, is my point. Okay. So what is the definition of uniform continuity? Well, in order for a function to be continuous, it has to be continuous at every point. And so once you have that point, you talk about an epsilon delta relative to that point. This is similar to convergence of a sequence. But one thing you can ask is that this epsilon delta works no matter what base point you choose. Okay? And that leads to the idea of uniform continuity. So here's the definition. And then instead of proving this theorem, I'm going to give you an example. So we're going to prove this later, maybe. It's in the textbook, but the proof, but still. So definition. A function between two matrix spaces is uniformly continuous. Uniformly continuous. If, and here's the epsilon delta statement. Instead of starting with for any x or x star, for any epsilon, there's a delta blah, 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 which was the definition of continuity, I'm going to start with epsilon. And x star is going to be at the end. For any epsilon positive, there is a delta positive, such that for any 2 points, x1 and x2 in X, if x1 and x2 are delta close, then their images are epsilon close. That's simple. Okay. It looks very similar to the definition of continuity, but they are not quite the same. In the definition of continuity, you wouldn't have this for all x1 and x2 in x here. You would have one point here, and then the other point would be all the way here. Okay? And we talked about how in logical statements, the order of quantifiers matter. Okay? So here's an example. If we take this for granted, I cannot come up with an example that is continuous but not uniformly continuous on a closed and bounded interval. So I'm going to cheat a little bit, or maybe not cheat perhaps, because I cannot just look at an interval like this and then look at a continuous function. It's going to be automatically uniformly continuous. But what I can do is I can get rid of one of the endpoints. Okay? And so this is the example that is given in the textbook. Consider this. This is a 0, 1 interval, 0 not included, 1 included, and take x to 1 over x. So the hyperbola. Okay, and immediately you would say, oh, you know, there's something bizarre going on here anyway. There's an asymptote at 0, and okay, so it's not that surprising that this function is not the best function. And so how does this look? This looks like this. So this is 1. And goes like this. Now, this function is continuous, okay? It's a continuous function. Why? Because, well, I mean, if you think about it, this is the ratio of a constant function and the function x, and x is never 0 in the 0 open, 1 closed interval, which means that this is a perfectly valid ratio of continuous functions. In particular, it is continuous. So this is continuous, okay? The claim is that it is not uniformly continuous. So it doesn't satisfy this property. So, claim not uniformly continuous. When you're trying to understand something like this, instead of starting with a logical sort of like order, I would suggest doing the following. Look at first what you're trying to control. All of these properties, continuity, uniform continuity, blah, blah, blah. It's all about controlling the distance between values, so outputs. So I start with something like that. So if I were to look at f of x1 minus f of x2 in absolute value, recall in this case, this metric is nothing but the difference, or the absolute value of the difference. So I'm just trying to bound this value, okay? Now what is this? This is 1 over x1 minus 1 over x2 in absolute value. And then consolidating, I have x1 minus x2 divided by x1 times x2. I don't need to put here absolute values because these are positive numbers, okay? Well, the numerator I can bound, right? Because both x1 and x2 are values between 0 and 1, which means that their difference, well, is at most 1. So the numerator is bounded by 1. But this is not enough, okay? This is not enough because of the following. As I take x1 and x2 smaller and smaller, in other words, as I'm getting closer and closer to this problematic point, their product gets arbitrarily small, okay? Well, if the product of these two numbers get arbitrarily small, the denominator gets arbitrarily small, which means that the whole thing grows unboundedly. Which means that if I'm not given at least one of these points to anchor, I will just take smaller and smaller pairs of numbers, which is going to cause this value, which is what I'm trying to bound, to grow without bounds. Okay? So maybe, so this is the heuristic. Any questions about this? Now we can leave it at this, and maybe we can try to come up with specific values for x1 and x2 too. So what do I want? Perhaps, let's say, okay, so this is something you can do, okay? Consider, so fix n, positive integer. Look at x1 to be 1 over n, x2 to be 1 over n plus 1, okay? The point is that for arbitrary n, I don't know where these are, but depending on what I'm trying to do, I can take n as large as I want, which is going to cause these to be as small as I want. Then this is what happens. What is this? Well, this is just a reciprocal of this guy, right? 1 over n is n, and this is n plus 1. That's not what I want. I want something else. Let's do 2n. That still works. So n minus 2n in absolute value, which is just n. Okay. So if I were to take an epsilon, also note that the difference between these two get arbitrarily close. Okay, x1 and x2, as I take n to infinity, well, both of them go to 0, which means that the distance between them, if I take n large enough, is going to be smaller than any delta that I might come up with. But ultimately, this guy is not going to be bounded. Okay, that's sort of like a more concrete way of arguing about this. So ultimately, when you're missing an endpoint, that's a problem. Okay, that's all you need to get from this discussion. Maybe if you have time later, we can look into this uniform continuity and how it relates. Possibly after handling integrals, Riemann integrals, we're going to look into series, and there we might have, it might be useful for us to look into those things. Okay. Any questions? Okay. So for the rest of today, I'd like to talk about function space. Function spaces, rather. Now, what do I want? I want to be able to take a sequence of functions with the same input and output and talk about that sequence of functions converging to some other function. And if possible, I would like to be able to say that that limit function too is continuous. Okay? And later on, once we start talking about differentiability, for instance, we would want the limit function to be differentiable and so on. So we want the limits to have the same properties as the terms of the sequence. So this is where we start. So let's look at this. Let's just start with an example. This was an example that I had given before. So here's a sequence of functions. Let's say they're defined on 0, 1, taking real values. At term n, I want f sub n to be the nth degree polynomial or monomial. This is a sequence of functions. And this is the one that is given in the textbook too, actually. Okay. So we would like to make sense of something like this. Sense of, well, limit as n goes to infinity, f sub n of x of this expression. Now, any guesses as to how one can make sense of this? There are multiple ways, and this is going to be important. But
you could have a 0 for everything except for that one, like single point where it's equal to 1, and then it's undefined above 1.
yeah, but what is the actionable thing there? You're saying plug in an x.
Like if x is less than 1, it's 0, because it's only defined on that interval. We could,
Yeah,
use
but
fancy stuff.
your idea is this. Instead of thinking of these guys as functions, let me just feed to it a specific point. Now it's a sequence of numbers. That limit I can take, and ultimately that gives me something. So one option, so option 1, fix x in the interval, and consider, this is kind of bizarre, but you fix the x, and now you have a sequence of real numbers. And consider the sequence. Let's write it like this. X bullet defined by x sub n equals f sub n of x, which is x to the n. In other words, take a number, you fixed it. Now look at all of its powers. That's a sequence of real numbers. Then look at its limit. I know what it means for a sequence of numbers to converge. Look at if it converges, take that limit, okay? How should I write it? So define this limit as the limit of the sequence of numbers. And then finally, observe that because initially you had fixed this x, quite possibly this limit is going to depend on x, which means that really this is a function of x. Defines a function. This defines a function f sub infinity from the interval to R, okay? So this is what you end up with if you do the intuitive thing, okay? And ultimately, this is going to be important to be able to do. And this has a name. This is what is called pointwise convergence. You have a sequence of functions. To find the limit, you feed to the sequence an input that produces a bunch of numbers. Then you take the limit as you would with any sequence of numbers. Okay? I'm going to give the definition later. Let's just first understand this. Slowing down because it gets complicated here. We were looking at sequences of numbers or abstract sequences. Now I'm asking you to think of each function as an element in a sequence. Okay, so this is pointwise convergence. Now, what is going on graphically? I had drawn this picture before, but let's slow down and do it again, because this is important. F bullet is a sequence of functions. And how can I visualize this? Well, one way to do this is to draw their graphs, okay? So this is the interval from 0 to 1. And I know that for any such function, its min, these are continuous, of course, because they are polynomials. Its min is 0, its max is 1. Okay, so this is my square, and I can draw their graphs on this square. When n equals 1, okay, f sub 1 of x is nothing but x. So it's a diagonal function. Doesn't look like diagonal, but this is the diagonal function. Okay. When n equals 2, f sub 2 of x is x squared. It's the parabola. Okay? So it's something like this. That's f sub 2. If I were to feed n equals 3, I would have the cubic. Cubics are, they're under this, the second order, at least between 0 and 1. So it would look something like this. And then f sub 4 would be even like this, even more bulbous. And eventually, what your colleague is suggesting is that as I take n to infinity, these pictures would converge to this picture. This thing should be f sub infinity. Why is that? Well, let's think about what it means to operate, what it means to follow this option 1. You're fixing an x. It's going to be arbitrary ultimately, and that's what defines the function as the limit. But you first fix one of these guys. Then you look at the vertical. So you see, this particular number over here is f sub 1 of x, the first term of my sequence of numbers. And then this point, the height, is f sub 2 of x, and so on. And then this point right here is f sub 3 of x, and so on. And ultimately, what your colleague was suggesting is that if I take x to be any number between 0 and 1, except 1, I'm going to have a bunch of heights like this, and they all, in the limit, decay to 0. And that is why f sub infinity of x should be 0, insofar as x is not 1. If x is 1, then for any function in my sequence, well, f sub n of x is 1 itself, because 1 is fixed under each of these functions. So no matter what happens, if I take, again, the limit like this, this stays the same, which means that this height should be f sub infinity of 1. Does this make sense? So how can we write this? You would say x is sent to 0 if x is between 0 and 1, 1 not included, and then 1 if x is 1. In particular, this is not a continuous function. Okay? now this is the trade-off. Often, if you do the obvious thing, the right intuitive thing, the limit is not going to be nice, okay? What you want is a notion of convergence in such a way that the limit function to itself is continuous. So you see, even though this is useful, intuitive, it has a name, blah, 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 the continuity property doesn't survive to the limit, in the limits, okay? So this is an important point. It's not continuous. Any questions about this? This is a very important point. Now, how to remedy this? There are multiple ways of remedying this, but the standard way of doing this is, in a sense, incorporating each of these x's into one definition, okay? And so this leads to the idea of the uniform metric. So I guess what I'm trying to say is that there's an option 2 here that's going to be called uniform convergence. That's going to imply option 1 if it holds, but in this case it's not going to hold. So remedy option 2, which is uniform convergence. Now, what does this entail? In a second, I'm going to give you the definition, but the idea is to come up with a honest to heavens metric on the space of continuous functions, or the set of continuous functions, and then look at convergence relative to that metric. Okay, that's why I've been investing so much time into this abstract notion of a metric space. Now it's going to come in handy. So here's the definition. Oh, even before that, perhaps let's look at this. If in this picture I had gotten rid of this 1, which is obviously the problem point, so let me restrict these functions into a smaller interval. Okay. Let's say now instead it's the same sequence, but I'm going to restrict it to, let's say, 0 to 3/4. So let's say this is 3/4. Okay. This specific number is not important, of course. What is important is that I'm far away from 1. Now, in this case, everything still holds. Option 1 still works. You can still look at points like this. Look at the limits. But in this case, you see, f sub infinity of x is going to be 0 for any x. And it is continuous in particular. So somehow, if you get rid of this 1, this bad point, everything works out fine. Okay. Okay. So here's the definition. Let's look at this. Let x, y be metric spaces. The uniform metric, or C0 metric, or you can also see the word supremum metric or L infinity metric. This has a bunch of different names. The C0 supremum, what else? Uniform L infinity metric on the set. Well, let's just look at all functions, in fact. On the set of all functions from x to y is the following. So what do I need? Elements in the set are functions. So I need to be able to say, what is the distance between two functions from x to y? This is what you do. Well, you first look at the distance relative to the metric for the output space between the values of f and g, and then you optimize. And the way you do this is by taking the sup over x's. Okay. There's a certain technical issue here. Okay, that's fine. There's a certain issue, but it's too technical, and I don't think if you can spot it, then I'll address it. But otherwise, I'm not going to say anything. So I define d sub c0 of f and g. So this is the distance between the functions f and g as this value. Okay. This is indeed a metric. But instead of verifying this, let's just look at the fact that this satisfies the so-called triangular inequality. Recall that this was one of the fundamental notions, one of the parts of a function being a metric. And after verifying this, I would like to draw some pictures as well, so that we have an idea as to how to imagine this. So, d sub c0 satisfies the triangular inequality. In other words, I want something like this. I want the distance between two functions, f and g, to be bounded from above by the sum of the sum of the distances of f to h, let's say, and h to some of the function g. So all three functions are from x to y. This is what is claimed. So this is what I want. And so, because the definition involves a sup, we're just going to play with the definition of sup. So if I were to fix an x, then f of x, g of x, and h of x are specific points in the output space. And I know that y itself is a metric space. In particular, this d sub y is a metric. In particular, it satisfies the triangular inequality. So I just use the definition of the triangular inequality with this particular metric. This is a number. It's a real number, non-negative. This too is a real non-negative number. If I were to optimize over x's, this would turn into a sup. This too would turn into a sup, which means that the right-hand side I can bound by the sup of this plus the sup of this. In other words, this would be bounded by the C0 distance between f and h, and likewise, this would be bounded by the C0 distance between h and g. In other words, for any x, I have a number, okay, that is bounded by this number. In particular, if I were to optimize this guy, its sup cannot exceed this value, and that's what I wanted. So I'm just using the definitions. That's the end. So it does satisfy the triangular inequality. It also satisfies the other two properties for a metric. Let's not spend time on that. Let's try to understand what this is about. In order to understand a metric, really what you want is an idea as to what it means for two things to be epsilon close relative to that metric. Okay? So this is what we need. And so I'm going to specify, I'm going to specialize to a single variable situation. So here's the example. Let's fix f to be, well, let's say it's just the identity. So x sent to x, diagonal. Let's say that g is some other function. And let's fix an epsilon. What does it mean? To say that this anonymous function g is epsilon close to f. This is what I'm trying to understand in this example. Okay, first I need to draw the graph of f. I don't know the graph of g because I don't know g. But I know the graph of f. That's f. Now what does this mean? Opening up again, this says that the sup of, well, now these are just the absolute value of the differences. Maybe I should write it like this. So the C0 metric, so C0 distance between G and F is nothing but this value. And I know what F is. It's just this. X. And I want my G to be such that it is epsilon close to F relative to the C0 metric. Okay, now how can I make sense of this, visually speaking? This is somewhat confusing, but because you're looking at two functions, even if I'm writing here x, you want to think of this as a height. Okay? So what you're doing here is the following. You're fixing an x here. This is the main diagonal, which means that the height at this specific point is also x. You want your g, this new function, to be such that when you draw its graph, at this slice, it's not farther than epsilon vertically compared to this point. So I don't know what my function g is, but what I know is that as I'm going from here to there, let's say, its graph has to pass. Has to hit this interval. So this interval is x plus epsilon x and x minus epsilon. But I want this to happen for any x, which means that what you need to do is you need to take the ribbon around the graph of f. So it's like this. So this length is plus epsilon. This length also is plus epsilon. So you can overshoot or undershoot, but you cannot go farther than epsilon, vertically speaking. Okay. So g, I still don't know what the function is, but in order for this bound to happen, it must be the case that its graph doesn't escape this epsilon ribbon. And the same intuition holds even in the abstract setting. Okay. Now the claim is, okay, so if this guy is a metric indeed on some function space, well, I can look at sequence of functions converging relative to that metric. Okay, now things are getting complicated. But my claim is that if you were to look at convergence relative to C0 metric, well, the limit of a sequence of continuous functions turns out to be continuous also. Okay, and that is option 2. We have 1 minute perhaps. Let me just write it like this. Perhaps I'm going to leave it to you as an exercise to verify that the first example we looked at, it's a sequence of continuous functions. It does not converge relative to the C0 metric. Okay? So the C0 metric is just strong enough to reject what we did before as true convergence of functions. We're going to spend more time on this because this is very important. But exercise. Not a convergent sequence. Relative to the C0 metric. It's going to reject this sequence as a convergent sequence. Okay? It is still yet to be shown that if a sequence of continuous functions converges relative to the C0 metric, then the limit 2 is continuous, but we're going to do that after the midterm. Okay? And I think that's it for today. Thank you. I'll see you tomorrow. We have a review.